Hello there. I want to come back and look at our topic from yesterday, which is energy. Energy is the focus of everything that we're doing in the current unit, and as such, I think it's important to really get a grasp for what we're talking about here. We're going to focus on a couple of fairly straightforward concepts mathematically in this section, but I want you to be keeping in mind the big picture. Okay, so we said yesterday, this is a review from yesterday, that energy is the ability to do work. And really, when I think about it, I often say energy is the ability to do something, right? If I've got a battery, it can do something. If I've got sunlight, it can do something. If I've got gasoline, it can do something, right? So at the end of the day, energy really allows us to do stuff. Very scientific. Now, yesterday I talked about, two basic forms of energy, and those are really these two important concepts here. The idea of kinetic energy, which is something that's moving, which has energy because of its motion. Right now, that being the case, something that's moving, if it has more motion, if it's moving faster, it should have more energy, and it will. And if it is bigger, if it's containing more mass, it will also possess more kinetic energy. And that brings us to our equation from yesterday for kinetic energy, which is a half mv squared. Right, which involves mass and speed. The other main type of energy is stored energy or potential energy. Right, and for stored energy, there's a number of different ways that energy can be stored. Again, in terms of, we're going to talk today largely about gravitational energy, but gravitational energy is potential. If I've got a book up on the bookshelf and it's sitting there, then all of a sudden the city bus goes by, or the dump truck or the garbage truck goes by, and the whole house shakes a bit and the book falls off the shelf. That book now had energy. It has the ability to do stuff, and I know it's going to get faster until it hits the floor and makes a terrific noise that might wake somebody up or cause someone to come running and wonder what's going on. But there was energy in that book while it was sitting there on the shelf. Right? That energy will be there, stored there until something uses it, right? Till something converts that potential energy into something else. It could be there for years, right? Maybe you've got a book. I've got a book on my bookshelf here, which is an old grade 10 book that I used probably 10 years ago. It's sitting here on my bookshelf in front of me, and it's got potential energy because it's sitting up there on my bookshelf, right? And that potential energy hasn't gone anywhere. It's still got that energy that it had 5 years ago, 8 years ago, 10 years ago when I first put it up there. And the question is, how did it get that potential energy? Well, I gave it that potential energy. Right? Whatever I ate that day contained energy in my food called chemical potential energy. And when that chemical energy went into me, I used that energy to create potential energy in that book. Right? So chemicals contain energy also. Where are they in this whole mix? Hopefully somewhere. There it is there. So chemical potential energy is a whole lot of different things. Food, fuel, like gasoline. There's molecular energy stored up in any of a number of different things and chemicals. So there's a lot of different ways that we store up chemical energy. You can see the person here with the bow and arrow, right? And with that arrow being pulled back, there's energy stored up there. It will stay there as long as that person is holding it, and the second they release it, that potential will be released, right? Okay, remember, it's potential energy. That potential will be released, just like the book on the shelf, just like the gasoline in my tank, just like the food in my fridge, right? It will stay there in that food until it gets released and converted to another form of energy. So I want to quickly go over a couple of questions from the homework looking at kinetic energy. So yesterday we said for kinetic energy, we derived the formula mathematically, and the formula for kinetic energy, one of the nice easy formulas in physics, half mv squared, allows us to calculate how much energy an object in motion has using its mass and using its velocity. Mass and velocity. No direction. It's not a vector quantity. It's a scalar quantity. And again, it doesn't matter what direction the V is, the object will have the same amount of energy. Whether it's going north or south or east or west, it will contain that same amount of energy. And the units, remember, are named after James Joule, so our units are in joules for kinetic energy. Now I left you with, I did this problem yesterday, I left you with these sample problems for 1.2a. I'm very quickly going to do one of them. Okay, I'm going to very quickly do question 2 in 1.2a. Okay, question 2 says, a dynamics cart. Okay, so you normally do labs using carts that have really good wheels on them with good bearings, very low friction. They're called dynamics carts. We use them for studying dynamics, forces. And by having little friction, we can study the other forces that are being applied to the object and say, well, we can kind of ignore friction because it's so low in this object compared to my push or something else that's pushing on it. So it says a dynamics cart has a kinetic energy of 4.2 joules. Okay, there's my kinetic energy. It says it has a speed of 5 meters per second moving across the floor. And what is its mass? So very simply, I'm going to take my formula, substitute my given information in, and solve for m. And I'm going to get an m value of 0.34 kilograms. Okay, that's it. Half mv squared. All right, so you're going to like Chapter 5 because the math is really pretty straightforward. It's hard to make this stuff difficult. I could try, but I probably can't make it very difficult. Okay, the second question that I left you with from the homework, and again, I also left you with all these questions here in our textbook, and I suggested that you do 7 and 8 first because they're solved for you, and then to go and do these 7 questions here on page 242 in our book. Then I also came to the work energy principle that says whenever energy changes in an object, the amount of energy change is representative of the amount of work that's been done. Now again, we derived that yesterday and we looked at how that works, and I did a sample problem yesterday, which is the sample problem 1 here, and I assigned questions 1 and 2 here for 1.2b, and I'm going to do question 2 again just for a minute. It's a little more work than the last one, but really... Okay, so this is 1.2b, and this is question 2 again. Question 2 says, a 52 kilogram ice hockey player, so let's get my ice hockey player here, get some skates going on, 52 kilograms, is moving at 11 meters per second, so there's the mass. V is 11 meters per second, and says this hockey player is going to stop in 8 meters. Okay, so this is a V1, and I'm going to have a V2 here, which is 0, and I have a delta D, which is 8 meters. Now, if I, how am I going to look at this? I'm going to say, well, I see mass and velocity. So if I look at this hockey player when they first start out, okay, before he or she puts on the brakes, right, they have kinetic energy. So if I find the kinetic energy at the beginning, let's say EK1, it's a half m V1 squared, which is 1/2 of his 52 or her 52 kilograms times 11 meters per second squared, and I'm getting kinetic energy, I just calculated this a minute ago, of 3,146 joules. I know that at the end, there's no kinetic energy because we've stopped. So EK2 here, I guess, is going to be 0 joules. Now remember we said yesterday that whenever the kinetic energy of an object changes, it changes because work has been done to that object. In other words, a force was applied to that object over a distance delta d in this case. So I can calculate my work done here by taking my final kinetic energy minus my initial kinetic energy, 0 minus 3146, and I get a work done of negative 3,146 joules. Okay, so there's my work done. Okay, the question is asking though, what is the net force on the skater? Right, what is the net force? So if I know that my work is equal to negative 3,146 joules, but work is equal to F delta D, F is going to be negative 3,146 divided by my distance of 8 meters, right up here, 8 meters, and I'm going to get a force of negative 3.9 times 10 to the 2, oops, 3.9 times 10 to the 2 newtons. Okay, so there's my F net. Now, that being the case, I know that there was a force pushing back on the skater, causing the skater to slow down to a stop, applying a force in the opposite direction to the direction of motion, which is why our work is negative 3,146 joules. Okay. There's a B part of this question. The B part of this question says, what are 2 reasons that you could predict that the net work on this skater must be negative? Well, the net work has to be negative because you know that in order to slow down, the force has to be in the opposite direction to the direction of motion. The force has to be negative if the displacement is positive. So for sure, F net, work is going to be negative because F net has to be negative. The second thing that you know for sure the work has to be negative is at the end, the energy is gone. So I'm starting with energy that is going to be gone at the end. So in the process, if I take final minus initial, it has to be negative, right? When I take EK2 here minus EK1, final kinetic minus initial kinetic, where the final kinetic was equal to 0, right? It has to be a negative answer, telling me that I have to have negative work being done. So negative work is being done for sure because kinetic energy is dropping. Also, because the applied force we know is in the negative direction, causing the object to slow down. Okay, let's go back to our notes here, and let's quickly, before I go any further, just let me remind you, I said yesterday that I was going to put some office hours up from 10:30 to 11:30 on Friday. I'm not planning on doing a note. I will probably take up some homework questions, and I'll be there to help anyone who has specific questions. And I will record it and post it. Right. So let's continue on with today's note. So today's note is about gravitational energy. Gravitational energy is like that book that I was talking about a minute ago, sitting up on the bookshelf. Right. It's energy that is potential. Energy that is potential. It is stored energy. It's there in the object. Right. Just like that gasoline in your tank. Right? The energy is potential. It is stored. That would be chemical potential energy. My textbook here has gravitational potential energy. It's stored, in this case, not because of chemical bonds, but because of where the object is located. Right? The reason why my book has potential energy is because of where it's located. And the reason why it has potential energy, and quite a bit, is because of where it's located compared to its environment. So how high is that textbook above its reference point? The reference point would be the 0 point where all the gravitational or potential energy is gone, which is, again, for most cases, the floor below where that object is. So if I'm talking gravitational potential energy here, we're talking about the energy that's stored in an object because of how high it is above the surface. Now, in order to get that textbook up from the floor, if I picked it up off the floor where it has no gravitational energy, right? It's not going to fall from the floor. Right? It's sitting there. It's as low as it can get. But if I had to get it up to the bookshelf, I have to do work to it. Right? I have to apply a force over a distance delta D to get it up onto that bookcase. Now I know the amount of force that's required to lift that 1 kilogram book is 9.8 newtons, because if the book is being pulled down by gravity and I want to put it up on the bookshelf, I've got to overcome gravity. There's not going to be a net force because I'm not causing it to accelerate. There's not going to be an unbalanced force. There will be a net force of 0 because my applied force will be equal and opposite to gravity. So in order for me to push that book or raise that book up onto the shelf, I have to do m times g of force applied to that book. And if delta D is how far I've had to lift it from the floor to the bookcase, then my definition of work is F delta D, right? Force times distance. Work is done when a force is applied to an object to move it a distance delta D. And I know that work is also equal to the change in energy. So when I apply a force and move it a distance delta D, I'm going to transfer energy either to or from. In this case, the force is in the same direction as the displacement, so the energy is going to be positive. I'm giving it positive energy, and when I'm done, if it started with 0, then the final energy that it has at the end is going to be F delta D. It's going to be the amount of energy that it has, but remember, F is mass times 9.8. So if delta E, which is Eg final minus Eg initial, but when it was on the floor, Eg1 is equal to 0 because it's sitting on the floor, means this whole thing disappears. And what that tells me is that the gravitational potential energy that's in the object at the end is equal to F delta D, which is equal to mg delta D. And the distance that I'm talking about here is how high I have raised that object. So delta D now becomes height. So I've now got a new formula, which is going to become our second really important formula, and a simple one for this unit, which is the formula for gravitational potential energy. And it says an object with mass m and at height h above the surface below will have Eg mgh of gravitational energy in joules. Notice m has to be in kilograms, g will be what we know it to be, and h is the height that the object is going to be, or the delta D that I raised the object vertically. So if I look at 1.2c down here, 1.2c, and I'm going to look at the sample problem for 1.2c. It says, what is the gravitational potential energy of a 48 kilogram student? Let's just go to 1.2c. What is the gravitational potential energy of a 48 kilogram student at the top of a 110 meter high drop tower ride compared to the ground? Right? Remember, I'm always talking about how high I am above what. In this case, it's above the ground below in the park, in the amusement park. So let's go to our whiteboard here. And I know that this is sample 1.2c. And it says the mass of the person is 48 kilograms. Their height is 110 meters above the ground. And the question is, how much Eg do they have? right? What's the gravitational potential energy? So given and required. I know my gravitational energy is mgh, so I can solve. So there's my required and my approach. Here's my formula. So to solve it, e.g., very simple, 48 times 9.8 mg times h, and I'm getting a gravitational potential energy of 5.2 times 10 to the power of 4 joules. Okay, that's it. So we've got these two very simple formulas now for putting together analyses of the energy components or energy associated with objects because of one, where they are, their height, and number two, how fast they're moving. Both of them require a mass component, because the more mass an object has, the more energy it's going to be carrying. Okay, so let's go back to our notes here. So there is the sample for 1.2c. I'm going to assign practice question 1 there that was right beside the sample. I'm also going to ask you to go back in our textbook and look at the samples that have been done for you, 9, 10, and 11. Read the question for yourself and do them on your own, and then go back and do questions 36 to 40. Those 5 questions, there's 1 or 2 in there that are really tricky. I think 39 and 40 or 38 and 40 are really, really tricky. You'll kick yourself when you see how easy they are, but to read them, it doesn't seem to make sense. Now, the last piece here talks about something called mechanical energy. So mechanical energy says when I'm talking about an object, let's say I'm kicking a soccer ball, and when it's here, it has 2 things going on for it. It's got a certain amount of gravitational energy, and it has speed, so it has kinetic energy. The combination of these 2 energies will always be related in a way that they're very easily interconvertible. They both become part of what's called the mechanical energy. And somebody who becomes a mechanical engineer isn't a mechanic who works on a car or a mechanical engineer that works on a train. It's a person who's studying the motion of any type of object, including frictional forces, including any aspect of what can affect the motion of an object. And in most cases, it comes back to these 2 components. And it turns out that in order to analyze the mechanical energy of an object, we're looking at both of these added together, right? The amount of gravitational energy and the amount of kinetic energy. And in the next section, 1.3, we're going to look specifically at how mechanical energy can be conserved in the motion of an object. As an object is losing gravitational energy, right, it's falling, it will be gaining kinetic energy. It will be getting faster. Or if an object is thrown up, as it gains kinetic energy, it will slow down and lose kinetic energy. So we're going to see that there's a relationship between these 2, and together we're going to add them up to make up this new concept of mechanical energy. Okay, so there's the summary there at the end of 1.2. Again, that's back in our samples and practice questions package, the other set of documents for this unit on energy. And then there are 1 to 6 questions on at the end of section 1.2 there. There's the summary, right? Again, just reminding us what is everything that we've talked about in this section 1.2. And then what are the 1 to 6 questions here? Looks like there's a roller coaster or something going on. So again, you get to look at those 6 questions also. All right, so I'm going to stop there for tonight. A nice short lesson, nice easy lesson. Half mv squared and mgh, kinetic energy and gravitational potential energy. All right, so I will leave it there. Hopefully I will see you on Friday for an office